Howdy. Like I mentioned many times, it's about learning. And I was searching something about susceptibility. And I don't remember exactly how I ended up here, but I ended up here. Tutorial: a beginner's guide to interpreting magnetic susceptibility data with the Curie-Weiss law. And interestingly enough, it's not that old and it's open access. So, I just want to read a little bit and then I will leave it there because I just wanted to show like what I mean by reading. I think I have to read this many times before I get like what they mean and stuff. I don't know. But let's have a listen to that. Abstract. Magnetic susceptibility. Yeah, this starts very good. Magnetic susceptibility. Measurements are often the first characterization tool that researchers turn to when beginning to assess the magnetic nature of a newly discovered material. I just want to mention that I am simultaneously trying to get my head wrapped around this transmutation of the elements, the structured atom, etokal, and now this also, amongst many other things. Sometimes I spend some time with something and then I switch to something else because I feel it. I don't get it. I have no idea what they're talking about. And sometimes just how it's written alone can be like just there are thousands of words you've never heard of and stuff like that. It's just interesting. Breakthroughs in instrumentation have made the collection of high quality magnetic susceptibility data more accessible than ever before. However, the analysis of susceptibility data remains a common challenge for newcomers to the field of magnetism. While a comprehensive treatment of the theoretical aspects of magnetism are found in numerous excellent textbooks, there is a gap at the point of practical application. Yeah, it might be like a double layer. Where we were inspired by this obstacle. I like people who are inspired by obstacles. To put together this guide to the analysis and interpretation of magnetic susceptibility data with an emphasis of materials that exhibit Curie-Weiss paramagnetism. Magnetic materials are of tremendous importance in both fundamental science and applications-driven research. Every research should be application-driven. The experimental toolkit for characterizing magnetic materials continues to grow year after year with advanced new experiments providing remarkable insights. However, for newly synthesized materials, there is one indispensable characterization technique that is as old as the field of magnetism itself. Magnetic susceptibility. Maybe this is how you pronounce it. Which is the quantity that relates a material's magnetization, M, to the strength of an applied magnetic field, H. In this tutorial, we will proceed with the conventional usage, which assumes that those two quantities are linearly related, which is typically most valid at high temperatures and low fields. In very general terms, magnetic susceptibility measurements tell you how your material responds to an applied magnetic field, which can be used to unveil the magnetic identity of your material. Susceptibility measurements can be performed in a direct current DC field, giving insights on the static magnetic properties, or an alternating current AC field in order to probe the dynamic properties. For more than 100 years, the preferred method for measuring magnetic susceptibility was based on determining the apparent weight of a sample in a magnetic field, as Duguay and Faraday balance techniques. However, in the modern era, more precise measurements have been unlocked through the advent of the SQUID, superconducting quantum interference device, which is obviously in box number 1. Magnetometer and its subsequent commercialization. Yes, many complicated words, especially susceptibility. Why I'm reading stuff like that is because I want to find out what's the thing about wide rivers, how they interact in the geomagnetic environment, how they react in a geomagnetic environment which changes rapidly and radically, and by order of many magnitudes. So, I tried to search quickly a video which I watched today. It's from this same brainiac guy. He has very many interesting videos. And I wanted to show you something. What element is attracted most to a magnet? Let's have a listen. Here makes a very nice intro. Because he's measuring the magneticity of those objects in different temperatures. So, it's not only about wide rivers, it's also about the weather, about the surface conductivity anomaly in Finland, about the Kursk magnetic anomaly in Russia, about many other conductivity anomalies on Earth and stuff like that, which are in the crust, the stuff mountains are made of. As we go into winter, the overall temperature is different, so the environmental changes in order or in like the geomagnetic. Is it geomagnetic? No. Geological magnetic. Things change. The rocks, they freeze. There's a temperature difference of some 10 degrees in this video. And it's very interesting.
Hi, which element is attracted the most to a magnet? Is it a clear winner, or is there any competition for it? I will test the best candidates at room temperature and an outsider just below that temperature in 4 different experiments. Going into this, I thought there would be a clear winner, but I was surprised by the results. Maybe you will be too.
So now let's just jump. I went a bit forward.
Again, we see nickel winning clearly over gadolinium at 23 degrees Celsius. But cobalt beat iron? Now I am confused. Is cobalt more attracted at a distance than iron? We need to include one of my favorite tests. The long distance test I call the water bath run. Working with ferromagnetic elements in this test for the first time, I wanted to get a feel for how long I could make the water bath. I didn't film it, but I wasn't.
Yes, check this out if you want to. And I think that's all very interesting. And how is this applicable, applicable to weather? It has to. There's, I don't know. It's very interesting. There has to be differences. Like I said, there's so much to learn. That's yeah, much work. But let's see. Maybe one day we figure it out. Why not? Who told you or who tells it? No, not possible. Why not? How does. Yeah, I think it's very important. Anyway, I leave it here. Thanks.